Today we study X25NQ. This is for the preparation of X25Q. So you can download the PDF file of this lecture by visiting our K-pop digital library. The address is kpope.org, kpop.org. You can click the X series in the table of contents. Almost at the end, we have X25, Kinetic Theory of Ideal Gas. If you click this, you can find the main textbook for X25. And if you click this, you can watch video for this lecture
이번 시간에는 우리
in Korean. And if you click the button next to E, you can watch the video
today we study
recorded
kinetic theory of
in English. And in the middle, you can click this to return to the K-pop digital library. And then if you still have not subscribed the K-pop YouTube channel, then please click this and you can visit the K-pop collaboration YouTube homepage and click to subscribe. Okay, let's begin with our today's lecture. It is a very short. First, explain the central limit theorem by making use of the following figure. The plot shows the binomial distribution weighted by square root of n divided by 2 to the n. Explain why it is important in thermodynamics. This binomial distribution is mainly for the probability of finding n cases in the serial throw of p equals 1 half and q equals 1 half, that is 1 minus p. We have an event either up or down, or head and tail when you throw a coin. And if you try a number of trial, n reaches to infinity, the distribution of finding up, let me call it k, and finding down, that is n minus k, the probability can be computed by the weight of this. So if you throw once, there are two cases, either up or down, and each throw has the two cases. And if you throw by n times, you have a multiplicity of 2 to the n. Among them, if you have n up and n minus k down cases, the number among n such identical trial, if you have k events of up and n minus k events of down, can be computed in such a manner. A simple way to find out this rate or this probability is as follows. Every throw has a probability of finding up or down is 1 half. So we try n times. So let's focus on the up. had cases. Okay. Then among the n such a trial, we have, for example, only once, then either this or that. If you try twice, up, down, up, down, and down, up, and down, down. 4 cases. So 2 cases, 4 cases, and 3, up, and so on. Okay, so 2, 8 cases. Here, everything up has only a single case. But up and down, when you have n equals 2, you have 2 cases. Up first and down first. So how can I compute this multiplicity? So we have 2 cases, 2 factorial. Among them, we do not have anything the same. So 1 factorial, 1 factorial. In case we have 3 trials and 2 ups and one down, the multiplicity of these kind of cases can be computed. I have thrown the coin by 3 times. So we have 3 factorial and we have 2 identical ups and a single down. In general, if I throw the coin by n times n factorial, k ups and n minus k downs, they cannot be distinguished. They cannot be distinguished each other. So if you exchange these two, it doesn't change at all. So that's the reason why this kind of binomial coefficient appears in the computation of the binomial distribution. Okay, so if you increase the number of trials capital N, then the distribution is concentrated at the central value depending on the probability distribution. If both of them are the same, the central part is exactly the same as 1/2. If it becomes 1, it is concentrated at the central value. This is called the binomial, the central limit theorem, using the binomial distribution as n goes to infinity. Okay, in macroscopic behavior of the statistical system consisting of many molecules, then we find the central limit theorem works because a number of trials involved with identical particles macroscopic system is satisfying the central limit theorem. Next, you might need this practical information. This is a periodic table. You can click this to find an example of periodic table, but it is public everywhere. Usually, we have atomic symbol, and there's a number. This number represents the ID for each atom, and the unique number. This unique number is identical to the number of protons in a single atom. However, the number of neutrons in an atom may vary. We call these various atoms with the same number of protons but with a different number of neutrons. We call them isotopes. So because there are various isotopes, we need to make an average, weighted average depending on the population of isotopes. So in our practical calculation involving chemistry, some interaction, chemical interaction, you need to know about that. It's a very popular thing to consider in considering the mass of an atom. We usually use carbon atom. A single carbon atom has 6 protons in it, and usually they have 6 neutrons to have 12 nucleons. Nucleons are either proton or neutron, but happen to be the carbon atom usually has a single carbon atom that usually has 6 protons and 6 neutrons. However, that's not all. That's not exclusive. Let's see. We have a practical unit that is called Unified Atomic Mass Unit, U, or it is also called the Dalton. Is the average of the proton rest mass and neutron rest mass. In many cases, the order of number of protons and number of neutrons not always the same, but their order, they are of similar order. So it's practically useful to take the average of the proton mass and neutron mass because not it is not always true that number of protons and number of neutrons in it in a single atom. We need to choose a standard. The standard one is a carbon atom. For example, carbon has 6 protons, and this is mass number 12. 12 is the number of nucleons in a single atom. So C12 atom has 6 protons and 6 neutrons. So it is very, very useful. It is convenient to define one Dalton based on this atom. 6 protons, 6 neutrons. So sum of weight of this divided by 12 is defined by the 1 Dalton or unified atomic mass unit. In terms of the rest mass, it is about this. Sorry, where c is the speed of light. Okay, so this unit is based on the special theory of relativity. So MeV is the energy divided by speed of light squared is the rest mass. So it is practically useful to remember that if you multiply a very large number called Avogadro's number to this tiny number that is the average mass of a single proton and a single neutron is almost the same as 1 gram. So this Avogadro's number is designed to match the mass of a sample of uniform materials consisting of single atoms by replacing the mass number with mass number multiplied by just simply gram. Okay. So 1 Dalton is the average of them. And then we can separate it into 2 pieces, the proton mass and neutron mass. You can find the neutron mass is slightly, very, very slightly greater than the proton mass. By the way, in nature, a single atom is not, or the one mole, it is not having mass number 12.011, something like that, because number of protons and number of neutrons are integers. The, the reason why we have such kind of number when we have a sample of a very large number of atoms is that they have some population distribution. For example, two stable isotopes exist for C6. Its mass is 12 and mass number is 13. And C12 has the population, it's 98.9 at 8.89%, and the C13 is a rare but not really significantly rare. It is about 1%. So if you average, weighted average of these two masses, then you will find it is 12.01, something like that. So if we return to this periodic table, we have a mass that is not an exact integer. Instead, we have some additional digits. The reason is that we have averaged, weighted average. We have made a weighted average. So that's it for this, and it is useful for solving X25Q. That's it. Thank you.